The Solaris Lentis features a lenticular disc geometry, measuring 20 meters in diameter and 16 meters in total height. Its structure is divided into three main zones: the upper dome, central core, and lower disc. The upper dome houses the sensor crown and electromagnetic projection lattice, while the central core contains the superconducting tri-ring stack. The lower disc is dedicated to magnetohydrodynamic plasma acceleration. This high-volume curvature is meticulously engineered for field symmetry and superconducting stability, ensuring minimal turbulence and optimal performance. The hull thickness varies between 12 and 40 centimeters, tuned to resonate with the superconducting ring harmonics for structural integrity. Delving deeper, the Solaris Lentis is organized into three structural zones, each with a distinct function. The upper dome is responsible for field projection and houses the sensor crown, EM projection lattice, and field-sheath emitters. The central core is the heart of the craft, containing the toroidal, poloidal, and axial superconducting rings, all cooled by a closed-loop LN2 system. The lower disc is engineered for plasma acceleration, featuring plasma sheet channels, Lorentz vector thrust grids, and boundary ionization layers. This triple-zone architecture is key to the craft's stability, field control, and propulsion efficiency. The Solaris Lentis employs advanced mathematical models to optimize material performance. The effective thermal conductivity is calculated using a weighted gradient of the CMC, MXene, and metamaterial layers, ensuring controlled heat flow and a stable superconducting environment. Additionally, the hull's resonance frequency is tuned to match the superconducting ring harmonics, preventing destructive interference from plasma oscillations, EM impulses, or flux waves. These equations are vital for maintaining the craft's operational integrity under extreme conditions. The heart of the Solaris Lentis is its triaxial superconducting ring stack, located in the central 4-meter core. This assembly consists of three orthogonal rings: the toroidal ring for primary magnetic confinement, the poloidal ring for plasma stabilization, and the axial ring for inertial symmetry. These rings are cooled by a multi-stage LN2 system and are supported by a power routing spine. The tri-ring configuration enables the generation of complex magnetic fields, essential for plasma confinement, thrust vectoring, and field sheath formation. Maintaining superconductivity requires precise cryogenic management. The Solaris Lentis uses closed-loop LN2 liquefaction, multi-stage vacuum insulation, and redundant cryopumps to ensure stable operation. Thermal shock suppression layers protect the superconducting rings from rapid temperature changes. This robust cryogenic system is essential for sustaining zero-loss current loops and preventing quench events, which could compromise field stability and propulsion performance. Field strength and stability are governed by precise mathematical models. The toroidal field strength is given by $B T = frac mu 0 I 2 pi r dollar, where $I is the current and $R the radius. The poloidal field uses $B P = frac mu 0 n I 2 r dollar, with $N turns and $R as the major radius. EM impulse frequency is $F = frac 1 2 pi, squirt frac km, where $K is field stiffness and $M the effective plasma mass. These equations ensure flux quantization, zero-loss current loops, and stable plasma confinement. The lower disc of Solaris Lentis is dedicated to plasma propulsion. Using MHD plasma acceleration, ionized air or plasma is accelerated through Lorentz force thrust grids and plasma sheet channels. Pulsed plasma sheets enable precise thrust vectoring, while boundary ionization reduces drag. This architecture allows for silent plasma glide, hypersonic flight, and vertical takeoff and landing (VTOL) capabilities, all controlled by advanced field modulation. Plasma generated in the lower disc is confined and accelerated by the combined action of the tri-ring magnetic fields and the Lorentz grid. The plasma flow paths are carefully shaped to maximize thrust efficiency and minimize turbulence. The boundary ionization layer ensures that plasma remains stable and contained, even during rapid maneuvers or transitions between flight regimes. This system is key to the craft's agility and silent operation. The field sheath envelope is a dynamic boundary that modulates plasma interaction with the hull. Electric fields evolve to dissipate shocks and reconfigure the sheath in response to flight conditions. The inertial tensor coupling between the sheath and the hull ensures smooth transitions between atmospheric, plasma, and vacuum modes. This system is essential for maintaining stability, reducing drag, and protecting the craft from high-energy impacts. The sheath harmonics are tuned to minimize Kelvin-Helmholtz instabilities and maintain a uniform plasma boundary. Magnetohydrodynamic MHD transitions are carefully managed with embedded equations guiding the evolution of the sheath under varying flight conditions. This ensures that the craft remains stable and efficient, regardless of speed or environment, and that the plasma envelope adapts in real time to external forces. Flight control in the Solaris Lentis is managed by a quantum AI core, which maps control inputs to field modulation commands. The system synchronizes plasma thrust vectoring, sheath reconfiguration, and regime transitions between atmospheric, plasma, and vacuum modes. Diagnostic observables and mathematical control models ensure that every maneuver is executed with precision, stability, and safety, regardless of external conditions. The Solaris Lentis features integrated flight control zones, each responsible for a specific aspect of maneuvering. Attitude, thrust, and mode control interfaces are mapped to the quantum AI core, allowing seamless transitions between flight regimes. Diagnostic data streams and control directives are displayed in real time, ensuring that the pilot or autonomous system can respond instantly to any change in conditions. Powering the Solaris Lentis is a hybrid system combining zero-point energy interfaces, high-density capacitor banks, and superconducting pulse conduits. EMIM pulse harmonics and frequency tuning are managed by the quantum core, while cryogenic cooling and thermal regulation ensure optimal performance. This energy architecture supports both routine operations and high-intensity maneuvers, delivering reliable power across all regimes. At the center of the power system is the zero-point energy interface, surrounded by radially arranged capacitor banks. Superconducting pulse conduits distribute energy throughout the craft, with EMIM harmonic overlays ensuring efficient power transfer. Cryogenic cooling loops and thermal regulation zones maintain system stability, while teal energy vectors and diagnostic callouts provide real-time feedback on power status. The hull of Solaris Lentis is a multi-layered shield, combining graphene composites, MXene shielding, and metamaterial skin. Each layer serves a specific function. The graphene composite provides structural strength, MXene layers offer electromagnetic shielding, and the metamaterial skin ensures radar transparency and field routing. Additional layers include a sensor coating, plasma field layer, thermal buffer, and radiation shielding, all working together to protect the craft and its occupants. Each material layer in the hull is optimized for a specific role. The sensor coating enhances situational awareness, while the plasma field layer interacts with the sheath for additional protection. The thermal buffer zone absorbs and dissipates heat, and the ablative substructure provides sacrificial protection against extreme conditions. The magnetic flux liner and EM field seal ensure that internal fields remain stable, while the vacuum wall and structural frame maintain overall integrity. The Solaris Lentis adapts to three primary flight regimes: atmospheric, plasma, and vacuum. In atmospheric mode, ionization assists lift and control, while dynamic hull shaping and plasma sheath modulation optimize stability. Plasma mode involves sheath reconfiguration for containment and thrust control, with cryogenic systems managing thermal loads. In vacuum mode, inertial navigation and pulse-based thrust take over, with radiation shielding and energy optimization ensuring safe and efficient operation. Transitions between flight regimes are managed by a mode control interface, which seamlessly shifts the craft's configuration based on environmental inputs and diagnostic triggers. The sheath morphs in real time, adapting to changes in altitude, speed, and external conditions. Mathematical models for lift, thrust, and propulsion efficiency guide these transitions, ensuring optimal performance and safety at all times. In atmospheric mode, The Solaris Lentis leverages ionization to assist, lift, and control. The hull's dynamic shaping and plasma sheath modulation work together to maintain aerodynamic stability. Sensor feedback loops monitor altitude, airspeed, g-force, and thermal gradients, while plasma channels adjust thrust for optimal balance. The result is a craft that glides silently and efficiently through the air, even at hypersonic speeds. When operating in plasma mode, the field sheath envelope is dynamically reconfigured to contain and control the plasma. EMIM harmonics are tuned for precise thrust control, while cryogenic systems manage the increased thermal load. Telemetry systems monitor field harmonics, power output, and sheath integrity, ensuring that the craft remains stable and responsive even in the most challenging plasma environments. In the vacuum of space, the Solaris Lentis relies on inertial navigation and pulse-based thrust control. The hull's amexine and metamaterial layers adapt to changing radiation flux, while energy optimization routines tune the capacitor banks and zero-point interface for maximum efficiency. System diagnostics continuously track radiation exposure, energy levels, and overall system status, ensuring safe and effective operation far from Earth's atmosphere. The transition between atmospheric, plasma, and vacuum modes is visualized in the flight mode transition map. Control overlays and regime transitions are clearly marked, with sensor thresholds and diagnostic triggers guiding the process. Field modulation and sheath reconfiguration are dynamically adjusted, ensuring that the craft adapts instantly to any change in environment or mission profile. The Solaris Lentis is equipped with advanced diagnostic systems, including photonic sensor crowns, plasma telemetry nodes, thermal gradient sensors, and radiation flux detectors. These sensors feed real-time data into the quantum AI core, enabling continuous monitoring of field harmonics, power output, sheath integrity, and system status. Fault detection protocols ensure that any anomaly is detected and addressed before it can impact performance. Diagnostic feeds monitor field harmonics, power output, sheath integrity, and system status. Threshold triggers and redundancy checks are built into the system, with an alert hierarchy that distinguishes between minor, critical, and catastrophic faults. Auto-reconfiguration protocols allow the craft to adapt its field and thrust systems in real time, maintaining operational integrity even in the face of unexpected challenges. Mathematical observables, such as thermal load, radiation, stress, and field integrity, are continuously calculated. The control feedback loop links sensor input to diagnostic feeds, fault detection, and control response. This adaptive logic ensures that the Solaris Lentis can survive and thrive in any operational regime, with real-time modulation of thrust, field, and energy systems. At the heart of the Solaris Lentis control system is the quantum AI flight core. This advanced processor predicts field behavior, synchronizes plasma and EM systems, and suppresses turbulence in real time. By integrating sensor data, mathematical models, and control logic, the quantum AI ensures that every flight is smooth, stable, and efficient, regardless of external disturbances. Plasma thrust vectoring is achieved by dynamically adjusting the Lorentz grid and plasma sheet channels in the lower disk. The quantum AI core calculates the optimal configuration for each maneuver, ensuring precise control over direction, speed, and stability. This system enables the Solaris Lentis to perform complex maneuvers, including VTOL, rapid acceleration, and silent gliding. The field sheath envelope can be reconfigured in real time to adapt to changing flight conditions. By modulating the electric field and plasma boundary, the system can dissipate shocks, suppress instabilities, and maintain optimal aerodynamic or plasma performance. This adaptability is crucial for transitioning between atmospheric, plasma, and vacuum environments. The zero-point energy ZPE interface at the heart of the power core taps into quantum vacuum fluctuations, providing a theoretically limitless energy source. This energy is buffered by high-density capacitors and distributed via superconducting conduits, ensuring that the Solaris Lentis always has the power needed for advanced maneuvers and sustained operations. Superconducting pulse harmonics are used to modulate energy flow and field strength throughout the craft. By tuning the frequency and amplitude of these pulses, the system can optimize propulsion, field stability, and energy efficiency. This technology is at the core of the Solaris Lentis's advanced performance envelope. The metamaterial skin of the Solaris Lentis is engineered to suppress radar cross-section and root electromagnetic fields. Negative index patches and tunable EM absorption make the craft nearly invisible to conventional detection methods, while also enhancing field control and structural vibration damping. The primary hull layer is a graphene-reinforced ceramic matrix composite, offering exceptional strength and thermal resistance. This material is key to withstanding the extreme conditions encountered during hypersonic flight and atmospheric re-entry, while also providing a stable platform for field and plasma systems. The MXing conductive lattice serves as the mid-layer of the hull, enabling tunable electromagnetic absorption and stealth optimization. This advanced material supports high-frequency EM-IM oscillations, contributing to both field shaping and radar transparency. The performance of the Solaris Lentis in different regimes is governed by key equations. Atmospheric lift is calculated as $L equals frac 1/2 rho v2 SCL dollar, while plasma thrust is given by $T equals K sum I n times B n dollar. In vacuum, propulsion efficiency is measured as $eta equals frac P out P in equals IV cos theta E ZPE dollar. These equations ensure that the craft operates at peak efficiency in any environment. Sensor arrays are distributed throughout the Solaris Lentis, providing comprehensive telemetry on field strength, plasma flow, thermal gradients, and radiation exposure. This data is fed into the quantum AI core, enabling real-time adjustments to field, thrust, and energy systems for optimal performance and safety. The Solaris Lentis is equipped with advanced fault detection protocols. Threshold triggers and redundancy checks ensure that any anomaly is detected early. The system can automatically reconfigure its field and thrust systems in response to faults, maintaining operational integrity and mission success even under adverse conditions. Redundant safety systems are built into every critical subsystem of the Solaris Lentis. From segmented superconducting rings to backup cryogenic loops and layered diagnostic protocols, these redundancies ensure that the craft can withstand and recover from unexpected failures, providing unmatched reliability in any environment. The true strength of the Solaris Lentis lies in its system-level integration. Every subsystem, from the superconducting core to the plasma drive, hull materials, and control logic, is designed to work in harmony. This integration enables the craft to achieve feats of performance, stealth, and adaptability that are unmatched in aerospace engineering. In summary, the Solaris Lentis VLX 2016H is a field-dominant aerospace platform that combines electromagnetic plasma propulsion, superconducting field shaping, AI-driven stabilization, and weak field GR sensing. Every aspect of its design is rooted in realistic, present-day technology, with a focus on reliability, efficiency, and adaptability. This dossier represents the pinnacle of Hartman-Class aerospace engineering, offering a glimpse into the future of advanced flight. The Solaris Lentis sets a new standard for aerospace innovation, but the journey doesn't end here. Future advancements may include enhanced Casimir engineering, more efficient superconductors, and even greater integration of quantum technologies. As research continues, the Hartman lineage will remain at the forefront of field-dominant aerospace design, inspiring the next generation of engineers and visionaries.